Preface. A number system is a system that lets us express numbers in writing. If it weren't for a number system, you'd have to use an infinite number of symbols to express numbers. As someone in the field of computer science, you should understand number systems which are frequently used in computers. You will see how number systems play an important role as you progress in this class and major. So if we take a look at some ancient number systems, we have the Chinese, Greek, Babylonian, and as you probably recognize, this is the Roman numeral number system. And this is what these different civilizations used to represent numbers. These are the symbols that they used. However, let's take a look at the system that we use in our everyday lives. And this is the denary, or as it's most commonly known as, the decimal system. In the decimal system, we use 10 digits to represent all numbers, and the reason for this is likely because we have 10 fingers. The digits that we use are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And the system uses 10 as its base number, so that's why it's called the base 10 system. Say I want to count from 0 to 10. Pretty easy, right? We have 0, 1, 2, 3, 4, 5, 6, 7, 8. You following with me so far? 9. What happens when we get to the number 10? There's no digit for 10. Remember, it's only 0 through 9. So when we get to 10, we have to move to the left. And when we do this, we have to increase the value of that place by 10. So note that base 10 uses 10 as the base. And then as we move to the left, we increase the exponent by 1, which increases the value of each place by 10. So a 10 is really 1 10 and 0 ones. We can also use the system to represent much larger numbers like 1853 or 1853. There's 1 1000s, there's 8 100s, there's 5 10s, and 3 1s in this number. So you should understand how this works because you've been doing this since you were little, since you were probably in grade school or even before that. But let's talk about something new. Let's talk about binary. Binary review, or should be. Binary or base 2 number system uses only 2 digits to represent numbers, and those are 0 and 1. Note that you cannot use 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s in binary. The only 2 digits available for use are 0 and 1. And even though we're just limited to these 2 digits, we can count to infinity using binary. Binary, but why? Why, Mr. Westphal? Why do we have to learn about this? Well, modern day computers use electricity to do stuff. Simple enough, right? There are billions of tiny transistors in a CPU, which are basically on or off switches that control the flow of electricity to other transistors. And the CPU uses these to add, multiply, divide, and etc. So to answer the question why, it's because it's simplistic. Simplicity, the on or off state of the transistor, can be represented by binary. Let me explain. When the transistor is open, essentially the switch is off and the electricity does not flow. And this is analogous to a light being off on a light switch when the switch is in the off position. Now, this is symbolized in binary by a 0. And when the transistor is closed, the switch is essentially on and the electricity does flow. So that's symbolized by a 1 in binary. So 1 is on and 0 is off. That's kind of how a transistor works in the CPU. And you got to understand that there's billions of these in that CPU. Now let's use binary to do something super basic. We're going to represent numbers, and we're going to start by counting from 0 to 10 in binary. To do this, we have to create what I call a cheat sheet. So we're actually setting up our place values. And note now that we're using 2 as our base instead of 10. So look there, we have 2 to the 0 power, then 2 to the 1, then 2 to the 2, and 2 to the 3, and so on and so forth. So we start out at 2 to the 0 at the far right, and as we move to the left, we increase the value of each place times 2. So our values are 1, because anything to the 0 power is always 1 no matter what the base. And as we go up, we see now there's 2, 4, 8, and so on. We're going to stop there for now. We represent numbers by putting either a 1 or 0 in each place in that chart. So a 1 in the place says multiply the base value by 1. And a 0 says multiply the base value by 0. Essentially, we want to add the values where the ones are in that chart. So let me show you exactly what I'm saying here, because this is a little confusing, but I think it's going to click as soon as I start putting these 1s and 0s in the places. So we're starting with the value of 0. What I want to do is I want to put either a 1 or 0 in each of these places. Okay. However, the values are 8, 4, 2, and 1. So starting from the left-hand side, I'm going to put a 0 in the 8's place, a 0 in the 4's, a 0 in the 2's, and a 0 in the 1's. That's telling me that there's 0 8's, 0 4's, 0 2's, and 0 1's in the value of 0, which kind of makes sense. Moving along, 1, okay, to represent 1, we're going to put a 0 in the 8's because there's no 8's in there, there's no 4's in there, there's no 2's, but there is a 1. So the decimal value of 1 is equal to 1 in binary. Okay, there's 1 in the 1's place. Note that you do not have to include any leading zeros in your answer unless I specify otherwise. And leading zeros are the zeros that are to the left of that first 1. Okay, here's 2. 0, 0, 1, 0. Okay, there's a 1 in the 2's place and a 0 in the 1's place. So the decimal value 2 is equal to 1, 0 in binary. Okay, let's look at 3. There's 0 8's, 0 4's, but there is 1, 2, and there was 1, 1. 2 plus 1 equals 3, and 3 is represented in binary by a 1 in the 2's place and a 1 in the 1's place. So 11 in binary is actually 3 in decimal. Isn't that crazy? Okay, going on. 4. There's a 0 in the 8's place. There's a 1 in the 4's place. And there's no more left. So we're going to put zeros. Okay? So 100 in binary is the decimal value of 4. Okay, 5. There's a 0 in the 8's. There's a 1 in the 4's. And there's a 0 in the 2's. And there's a 1 in the 1's. So 1, 0, 1 in binary is equal to 5. There's a 1 in the 4's and a 1 in the 1's. 4 plus 1 equals 5. Hoping this kind of makes sense by now. Okay, 6, 0 8's. There's a 1 4 and a 1 2. Okay, 1 1 0. All right, moving on to 7. There's 0 8's. There's 1 4. There's 1 2 and 1 1. So 1 1 1 is equal to 7. There's a 1 in the 4's, 1 in the 2's, 1 in the 1's. 8. Oh, we're finally going to use that 8. So instead of putting 0 there, we're actually going to put 1. and then the rest of these are 0. Okay, there's a 1 in the 8th place, and there's a 0 in the 4s, 0 in the 2s, 0s in the 1s, so 1,000 in binary is equal to 8 in decimal. Now 9, we're going to say there's a 1 in the 8s and a 1 in the 1s. 8 plus 1 equals 9, and 1001 in binary is equal to 9 in decimal. And then lastly, 10. So we're going to put a 1 in the 8s place and a 1 in the 2s place because 8 plus 2 equals 10. So 1010 in binary is equal to 10 in decimal. So I'm going to show you this quick video. It's from user Mathmo14159 on YouTube, and he basically made this apparatus to count from 0 to 10 in binary, and I think it's pretty interesting to see it kind of sped up. So here's an ironic t-shirt for those of you who like ironic t-shirts. It says there are 10 types of people in this world, those who understand binary and those who don't. Da-dunch. Do you get it? Do you get it? Think about it for a second. If you don't get it, 10 or 10 in binary is equal to 2 in decimal. So it really says there are 2 types of people in this world, those who understand binary and those who don't. Funny, huh?